We're moving on to a new chapter, everyone. Chapter 8, we're going to talk about periodic functions. This chapter only has 3 sections. The first section, we're going to talk about what sine and cosine look like as graphs, and then do way more than you're ever going to want to do with these graphs. And then we're going to talk about the other 4 trig functions next section. That'll be interesting. And then we're going to start talking about inverse functions. And people love inverse functions. You may have been even trying to use inverse functions so far, but have some patience. We'll get there eventually. So, as you may have noticed by now, I like to teach with examples. So here we go. Graph, sine of x. Oops, I forgot the y equals. So we'll just put the y equals part at the back. All right. And so you may say, well, section is graphing sine and cosine. How am I supposed to graph it? We haven't talked about that yet, Jason. Well, don't worry. Don't worry. We're going to do this how we graph every function that we don't know how to do. Not with the computer. We'll graph it by hand. And the way we're going to do that is we're going to make our axes, and we're going to make a little table. And our table is going to have x's and y's. So, one of our favorite places to start when we're graphing something is at 0. 0 is a great place to start. And you know what the sine of 0 is. By now, I think most of you are pretty comfortable with the sine of 0. We can look at the unit circle. 0 is 0 degrees, which is just right here. And sine is the y-coordinate. What is the y-coordinate right here? It's 0. So we've got a great spot already. So this is the x-axis, this is the y-axis. When x is 0, y is 0. And you may have noticed I haven't put any hash marks in my coordinate plane yet. That's because I don't know how this graph is going to go. That's a lie. I know exactly how this graph is going to go. But you don't know how this graph is going to go. So who knows where we want 1 is? Should 1 be way over here? Should 1 be way over here? Should this be 100? Who knows? Let's just plug in some points first. And so now we could plug in other points, right? I could plug in pi over 4 because sine of pi over 4 is 1 over root 2. But I don't want to graph 1 over root 2. Let's stick with easy numbers, okay? As long as we're doing the unit circle, well, let's do another nice number on the unit circle, right? That's pi over 2. What is the y-coordinate right here? It's 1. So when x is pi over 2, y is 1. So it's going to be way easier. Instead of having your x labels be 1, 2, 3, 4, and then going, oh, where the heck is pi over 2? Let's just make a mark at pi over 2. When x is pi over 2, y is 1. Let's say that's up here. This is 1. This is going to be negative 1. And then we can go this way. Let's count by pi over 2s. Oh, let's keep going. Another really nice point on the unit circle is when x is pi, the y-coordinate here is 0. So again, if one hash mark is pi over 2, this is 2 pi over 2, that's just another pi. Well, let's keep going. What is this one over here? That's 3 pi over 2. Again, just another pi over 2 along. I don't need to label every single one, right? We're counting by the same each time. We're going to now be down at negative 1. And then notice what happens after this. Notice what happens next. If we go another pi over 2, that's 2 pi. Oh, we're back where we started. 2 pi is going to be 0. Oh, I didn't make this long enough. 2 pi is going to be 0, and then we're going to keep on rotating, right? It's going to be 0, then it's going to be 1, it's going to be 0, it's going to keep on going. And in fact, we could also go the other way, right? We can go backwards as well. And if we look at negative pi over 2, that's negative 1. If we look at negative pi, that again is just 0. And so we've got this thing that's going to repeat over and over again. You might say it looks like a bunch of V's, but it's not actually a bunch of V's. You could plug in points in the middle, right? There's some other nice things. We know what sine of pi over 6 is. Sine of pi over 6 is 1/2. And that is 1/3 of pi over 2. So it's not a straight line. It's actually really curvy. All right. And it just keeps on going. Just keeps on chilling forever. Repeating over and over again. And that is what the sine of x looks like. The graph of the sine of x looks like a wave, and it goes on forever. Okay, because if we look at the unit circle, every 2 pi, it's just going to repeat. You're never leaving the circle. You're stuck on the circle. All right? So, that's that. Do example 2. No, just kidding. Let's call this part A. Let's do part B. Let's graph y equals cosine of x. And you might be saying, oh my goodness, Jason, I don't want to do this again. This is too much. Surely there's an easier way to do this. And yes, there is. One of the huge things in this section that you may hate or you may love, I love it, so hopefully you're like me in this sense anyway, is function transformations. Because I remember, the great trigonometry student that I am, I remember a little thing we talked about in chapter 7 called cofunction identities. And what that told us, so recall the cofunction identity, right? That cosine of x was equal to the sine of the complementary angle, pi over 2 minus x. So you guys remember pi over 2 minus x? This is a function transformation of the graph that we've already given. Okay? So the transformation here is that we add a pi over 2 on the inside, which shifts everything pi over 2 left. And then we turn x to negative. That's a horizontal reflection. So let's do this step by step. Using the graph that we have put blood, sweat, and tears into, hopefully not literally. Using the same graph, let's apply the function transformations to see what cosine x looks like. Again, we're not moving it up or down, so we can still have a positive one and a negative right here. And again, we still really care about hash marks of every pi over 2. Say this is pi over 2. Oops. That's pi over 2. This is the danger of doing math with a pen. So that's pi, 3 pi over 2. This is 2 pi, etc. Just like before. Now we shift everything up here, pi over 2 to the left. This point gets moved over here. And this point gets moved right there. This point gets moved right here, etc. And you're going to pick up the pattern. So this is what happens when we do the first transformation. And again, it keeps on going forever and ever. So we haven't done all the transformations yet, only the first transformation. But notice what was the second transformation, right? We moved everything pi over 2 left. But then the next is a horizontal transformation, which means we reflect about the y-axis. Well, notice this is already symmetrical with respect to the y-axis. If I reflect this graph, nothing changes. It's already a mirror image of itself. Okay, so we actually did both function transformations at once, and this is, in fact, the graph of cosine. The graph of cosine of x. And we didn't even have to use a table. We just used this. So essentially, the cosine and sine are almost the exact same graphs. This one's just bumped a little bit. Okay? And if you forget which one is which, just plug in 1 point, 2 points, whatever. You'll get a good idea for what it is. So these are sine and cosine graphs. You will become very familiar with these, for better or worse. So let's get into a mathematical definition. So again, like most of my definitions, I'll give you the mathematical definition. For purposes of this class, we're barely going to use the mathematical definition, so I'll give a more realistic definition afterwards, a colloquial definition, if you will. So, periodic function. A periodic function is a function f such that f of x plus p equals f of x for all x and some period, that's the second part of the definition, p. All right, so again, all this means is that if we add 2 pi Spoiler alert, the period here is 2 pi. If we add 2 pi to any x value, we'll get the same output. Okay? Let's look at this one. X here is 0. This is when x is 0, y is 1. If we add 2 pi to the input, 0 plus 2 pi is 2 pi. What is our output? It's still 1. Okay? And every single point on this graph, if you add 2 pi to the x coordinate, you're going to get the same y coordinate. All right? And that's all this means. Okay? So essentially, what this definition essentially means is that the graph repeats every period. So every 2 pi for sine x and cosine x. Also, I didn't make this point earlier, but when we're graphing this, and in fact, almost any application ever, we're going to be talking about radians. Okay? Nobody ever graphs anything in degrees, almost ever. I can't, and I say almost ever, not because I can think of an ever, but because I don't like to speak in absolutes without knowing for sure. But I cannot think of a single time when you would graph or really do anything in degrees outside of dealing with triangles. But graphs and applications are going to be in radians basically always. Okay? So it's very, very important to get very familiar with these quickly. Because essentially, for sine and cosine, all you really need to know is what shape they are, and they have the same shape. They're wavy. Okay? You need to know the shape and then only 4 points. Okay? Right? And essentially, these are the 4 points that you need for cosine. All right? And every pi over 2, it moves from 1 to 0 to -1 to 0. Okay? And it oscillates like that. And then again, I guess you sort of need to know where it starts. Cosine's going to start at 1, sine's going to start at 0. We're going to be using this a lot. Okay? So, change of pace. Because I mentioned function transformations earlier, and we really need to review them. Function transformations will save your life. Well, not maybe save your life. A bit of an exaggeration, but they're going to help you out so much in this section. If you're good with function transformations, you will essentially have such an advantage in this section. So on the other hand, right, if you're not good with function transformations and say, I need to review function transformations, send me an email. I can send you some resources that you can use to review function transformations. So let's start with a couple of function transformations. There's a lot. So let's look at some graph. A parabola. Everyone loves parabolas. Okay. So my question is, what happens to this parabola if I add a +1 on the end of it? And the answer is, well, I'll show you guys the answer. Let's see. What happened? Well, the graph it's the same exact graph. We just shifted it up 1, okay? We can see these right next to each other. The red graph is the original. The blue graph is the transformed graph. Just the same thing, but we booped it up 1. Okay, so if I asked you what would happen if we subtracted 1, should not be too surprising. Adding 1 moves it up, subtracting 1 moves it down. A lot of times when we talk about function transformations, we talk about inside and outside. This is adding and subtracting 1 on the outside of the function, right? We're squaring something, and then as a way over here is when we're adding or subtracting. So then the question is, what happens if, we don't do that. What happens if we add or subtract 1 on the inside of the function? And this, you might expect, okay, well, it's not going to go up and down anymore. It's going to go left and right. But be very careful which direction it goes. If we add 1, it actually takes it to the left, which is counterintuitive to a lot of people. Okay? And if you subtract 1, it moves the blue graph to the right. Oh, my right is not your right. You're right. Okay, and there's a bunch more function transformations, right? Like if we put a negative on the outside, it flips it upside down. If we put a negative on the inside, it flips it left to right. And again, flipping it left to right doesn't change anything here because it's already symmetric about the y-axis. All right. And finally, if we multiply it stretches it vertically, unless we do it on the inside, and then it compresses it horizontally. All right, so again, that's just a brief crash course in function transformations. Hopefully you remember this, but if you don't, feel free to reach out, and we'll also do a little bit more review as we integrate this with the course content. All right, so now let's look at some stuff. We're going to introduce what's called like a generic form of the sine equation. All right, and it's essentially y equals a times the sine of bx plus c plus d. So really, the astute observer will notice that this graph, this form right here, is just a bunch of function transformations, right? The plus d, we're adding the d on the outside. That's going to move it up and down. The plus c, we're adding that on the inside. That's going to move it left and right. That's going to be called the phase shift. The a, we're multiplying it on the outside. That's going to stretch it up and down. We're going to call that the amplitude. And the b is multiplying on the inside. That's horizontal stretching and compressing. That's going to be related to the period, okay? So all this stuff, you can memorize what I'm about to write down. Again, we are going to write this stuff down, don't worry. You can memorize this stuff, but if you understand function transformations, then no memorization is necessary, okay? So let's look at one of these. Again, let's start with our basic graph, sine x. You should be comfortable right here. Should be comfortable with what sine x looks like. So again, let's change the change a couple stuff right here. So in sine x, remember, every pi over 2 units, it's really good to have a grid unit of pi over 2 for sine. It goes from 0 to 1 to 0 to negative 1 to 0 to 1 to 0, etc. You get the idea, right? So we're going to talk about essentially what each of these things does. And we're going to start with the amplitude with a. So let's look at something where a is 2. Well, now, instead of going up to 1, it goes up to 2. And back to 0. And then instead of going down to negative 1, it just stretches the whole thing, doubles it everywhere. Doubles it everywhere should make sense. 2 is on the outside. So that's the first thing that we're going to talk about right here, okay? And that is called amplitude. So let's get into it. Oh crap, I'm going out of order. Anyway, for a graph y equals sine a times sine of bx plus c plus d, we know the following. So here's what I want you to do. We're going to do these one by one. So you're going to have 4 bullet points in your notes. And we'll fill these in bit by bit. Okay? But we're only going to do one at a time. So I'm going to fill in this first one, and then we're going to do some examples. And then we'll come back so that in your notes, they're all in one place, even though we're not going to do them all at the same time. All right? So I lied to you, by the way. And I want to go in the order of my notes. My notes were written that way for a reason. We're going to first talk about what happens if I put a 2 on the inside of the function, not the outside of the function. So you'll see now that this green, it oscillates much quicker, right? In fact, in the blue graph, it took pi before we got back to 0. But in the green graph, we get there twice as fast. Now pi over 2. In fact, we get everywhere twice as fast as it was before. Twice as fast is the 2. So conversely, right, what if we didn't double the speed? What if we halved the speed? Whoa. That is not what I meant to type. Hold on. What if we have the speed, right? Well, then everything goes much slower. All right. So now it takes pi units to get to our peak instead of pi over 2. Everything takes twice as long or half as fast. Talk about this as speed. All right. And again, if you think of sound, if you're familiar with like sound and stuff, this is changing the frequency. Amplitude and frequency affects pitch. Amplitude affects volume, if you want to think about this as noise. Okay. So this changes the frequency. And furthermore, right, let's go back to the nicer one to look at, right? Sine of 2x. Look at the blue graph. What's the period of the blue graph? We already talked about that, sine x. It takes 2 pi units for this graph to start. Here, hold on. Make it a little easier to look at, right? It takes 2 pi units for the graph to repeat. Up, down, down, up. Well, if we double the speed, now how long does it take to repeat? Now it only takes pi. It used to take 2 pi. We made it twice as fast. Now it only takes pi. Okay? So again, twice as fast does not mean it goes to 4 pi. Twice as fast means it happens sooner. It should be a smaller number, pi. Okay, and that's going to be our first property. That's called the period. Okay? So, the period, so let's see what happened. We had 2 pi, and then we multiplied by 2 on the inside, and the period went to pi. So the period is actually always going to be 2 pi, but then if we double it, this is going to get halved. If we triple it, this is going to get divided by 3. If we quadruple the speed, divided by 4, etc. In fact, we always divide by whatever number is right here. And again, even if that number is negative, that does some other stuff. So we're going to use absolute value. The period is always positive. Okay? So let's do some examples. Part example 2. English is fine. What is the period? So again, don't worry too much about this formula. I think memorizing 2 pi divided by b is maybe not so easy. But all we do is just divide the normal period by b. Normal period divided by whatever that coefficient's going to be. So what is the period of, let's look at a couple ones. A, as I'm writing these down, I'm going to write down all 3 before we go through the answers. I'm writing these down. Think about how you'd solve the period. F of x equals sine of 2x. We already kind of did that one, but that's fine. Part B is going to be g of x equals cosine of negative 1/2 x. And part C, oh, I don't have room for this. We're going to write that over here. Part C is going to be h of x equals 2 times the sine of pi over 6x minus 2 plus 1. You might say, whoa, slow down. We haven't talked about all these other things. And that's true. Because it doesn't matter, right? For any complicated sine function, the only value we need to look at for the period is the number next to the x. Okay? So let's do this. What's the number next to the x? 2. So you look at the absolute value, because again, it's always positive. The period here is going to be the absolute value of 2 pi divided by whatever number is next to the x, the coefficient of x. Well, the 2's cancel. We're left with the absolute value of pi. Don't need the absolute values. Absolute values just make something positive. So the period here is pi. All right. Over here, what do we have here? The period is again going to be the absolute value of 2 pi divided by the coefficient. The coefficient is negative 1/2. So now be very careful with your complex fractions right here. Dividing by 1/2 is the same as multiplying by 2. Negative goes away because absolute values. So we're left with 4 pi. If you don't believe me, do it out in steps. And finally, the last one. The last one's a good one. I like the last one. Period is going to be the absolute value of 2 pi divided by the coefficient, which is pi over 6. This one's a little harder to see, so let's do this one in order, or in some steps. It's 2 pi divided by pi over 6. We can think of 2 pi as 2 pi divided by 1. And then what we have right here is 2 pi over 1. Division changes into multiplication, 6 over pi. The pi's cancel. And we're just left with 12. Which is going to look a little weird. But we're confident mathematicians. And we are going to check our answers Goodness gracious, we got some crazy cats going on right here. They are getting super excited for trigonometry. They have to cool down. All right. Anyway, let's check our answers for these. So hopefully you remember what we wrote down. In the first one, we had sine of 2x. And we said that the period was pi. Well, look, this repeats every pi. Once we get to pi, it's the same graph as we did before. And then 2 pi, same graph as before. 3 pi, same graph as before. And remember, the period's not pi over 2, because here it goes positive, here it goes negative. That's different. The period is how long it takes until it starts repeating. Okay? Let's look at another graph. The next one, this was part B. Cosine of negative 1/2 x. Yeah, let's zoom out a little bit. Well, how long does it take until we start repeating? We start repeating here. That's 4 pi. Oh, that was our answer. Our answer was 4 pi. And if we go 4 pi in the other way, it also starts repeating to the left. Very good one, yeah. Whenever you divide by a number, it makes the period longer. Whenever you multiply a number, it makes the period shorter. Multiplying makes it go faster. And the last one was a real bonkers graph. It was 2 times the sine of pi divided by 6 times x minus 2 plus 1. Okay? So now this, well, this doesn't look bad at all. This just looks like another sine graph. We just move things around. And so let's find a point that's easy to look at. 0.82. All right, it's not that easy to look at. But what's this point? When do we start repeating? 12.82. What's the difference between these two x values? 12. That's exactly the period that we found. All right? And if we go over this way, it's kind of hard to see. If we go over this way, right? It's adding another 12. The period is 12. That's how far x has to go till we start repeating. And a little bit of, I did this on purpose, guys. I kind of tricked you putting this problem in here. Let's look at some other stuff. What's the smallest we have here? Negative 1. What's the biggest y value here? It's 3. What's the difference between 3 and negative 1? 4. We normally oscillate between negative 1 and positive 1, but now we're oscillating between, our oscillation distance has gotten doubled. Okay? This minus 2 is shifting the graph to the right. This plus 1 means that we moved everything up 1, right? If I got rid of the plus 1, it's the same graph, just lowered and now centered again at 0. Okay, again, if you remove the 2, it's the same graph, just slightly moved. Okay, and again, all sines and cosines really are the same graph. In fact, if I asked you what is the graph of this, there's no right answer. You could tell me this is a sine graph. You could tell me this is a cosine graph. It's both. Okay? Because, hold on. Because of this guy. Because of this guy, the cofunction identity. A cosine graph is just a transformed sine graph and vice versa. Okay? So, we already got the first bullet point. Well, let's do the second bullet point. The amplitude. The amplitude is the absolute value of that number in front. Okay? Just makes it taller or shorter. All right, and we've seen this before, right? We did this right here. This is what 2 sine x looks like. Well, if we made a 4, that should double it and make it twice as tall. Ah, it did. Make it a 6. It should go up to 6. Right? If we make it 1, it should go to 1. If we halved it, it should only go to 1/2. If we quartered it, it should only go to 1/4. All right. And so that's all amplitude means. It's how high and low does it go? How squished is the wave, or how big is the wave? If you're thinking about these as sound waves, then this is the volume. Okay. So here we go. Let's use this. I'm going to have to put this to the side, but not too far to the side, because we have example 3 to talk about. Oh! Sorry. False alarm. I was just demonstrating what a large amplitude would sound like. Audially. That's not a word. Okay. Example 3. Okay. Here we go right here. Find the amplitude and determine whether it's a vertical stretch or compression. I'm out of room, so I'm going to write compress. All right. This is not an English class. All right. I'm not going to penalize you for your English skills. Thank goodness. So here we go. F of x equals -4 times the sine of x. So let's remember what we just said in the previous bullet point. The amplitude is the absolute value of the coefficient of sine. All right. So the amplitude is just the absolute value of the number that's next to the sine, which is -4. Well, the absolute value of -4 is just +4. +4 is the amplitude. Okay. And then, well, what's the second part? Is it a vertical stretching or vertical compressing? And it's going to be stretching it because we are making it 4 times as tall. Right? 4 times as tall. That's stretching it. Okay, and that's all there is to it. Okay, let's do parts B and C. All right, real quick, we got g of x equals 1/2 cosine of x. You know the answer to that one. And h of x equals pi times the sine of x minus pi over 2 plus 3 arg, or whatever. Okay, exactly what was pointed out in the chat. If we're bigger than 1, then we're stretching it because it's getting bigger. If we're smaller than 1, it's going to be compressing it because it's getting smaller. As long as, smaller in absolute value. Right? -5 is technically smaller than 1, but -5 would also be a stretching. Okay. The negative, we'll talk about what that means later. Okay. So again, here, your amplitude is just the absolute value of 1/2, which is just 1/2. Okay. So we'd say it is getting half as big, so it's compression. Vertical compression. Right here, forget all this other mumbo jumbo. We'll talk about that later on Tuesday. All we look at is the number next to it, the absolute value of pi. Well, that's just pi. And again, don't freak out. Pi is just a number. Pi is approximately 3.14159.265. You get the idea. It goes on forever, but it's about 3. So that's bigger than 1. So it's going to be a vertical stretching. And again, I don't want anyone to take me for a liar. I don't want you to think I'm pulling the wool over your eyes. Take my word on. Actually, you probably should take my word on faith, since I am teaching this class. But you can dispute it. You can dispute it, right? Professor's not always right, but they probably know more than you do on some things. I gotta not get too political right now. But if we look at the normal graph of sine, right? Well, then the question is, well, if I have -4 sine x, does it get bigger or smaller? Oh, definitely getting taller, right? So you can see definite stretching going on with this blue graph. All right, and specifically, instead of having it peak at 1, it now has a peak at 4. The valley is now at -4. It is 4 times as tall, which is exactly what we said. In part B, we said if we have -1/2 cosine of x, again, I'm not even going to change this from a sine to a cosine because they're essentially the same graph, just shifted around a little bit. Now the blue graph is half as big. Instead of peaking at 1, it peaks at 1/2. All right. And similarly, we could look at h of x and we can see the same thing. Okay, so we know we did a good job. All right. And it's a good idea to have Desmos open, by the way. If you don't know this website, it's desmos.com. It's a good idea to have this website open while you're doing your homework. You can check your math very easily with it. All right. And checking your answers is a very good tool in math. All right. Go ahead and do that a lot. It will help. Okay. So let's close the day out with the last two bullet points, I think, and do one more example. And then we'll essentially have covered everything for this section, but we'll spend a long time on Tuesday showing you what kind of stuff we can do when we put this all together. So this is kind of intro right here. All right. So third bullet point right here. Let's talk about the phase shift. Okay. The phase shift, and this is the one that trips people up. Out of all three of them, let's skip that for now, okay? The vertical shift, is up d units, okay? So if we add a 5, it moves the whole thing up 5. If we subtract a 5, moves the whole thing down 5. D, most people are really good with D. So that's a little warm up. Because this one right here, the phase shift, these are the ones that usually trips people up. Because you might think, oh, it's just going to be C. Well, it depends on C and B because of the way that this formula is. There is another form to this that looks a little bit more complicated, but it makes the phase shift a little easier. Phase shift is what moves it left and right, and it's going to be C divided by B. Okay? C divided by B. And essentially the reason for that is because really when we do phase shift, we want to have this inside factored. Okay? So off to the side, you don't have to write this down, but off to the side, right? You have bx plus c. If you factor out a b from this, remember factoring is like division. If you factor out a b, you're left with x plus c over b. And that's really what we want to look at. Okay. But we don't like writing things in this form because it's kind of a little uglier. And this is usually a little bit more common to see anyway. Okay. So just remember c over b. This is the real one that can cause trouble. And it's only important for the, convention, by the way, speaking of different formulas, convention is to have a negative sign up here. Okay. And then C over B is moved right. It's right C over B. Up D, right C over B if there's a minus. So in essence, it's always going to be the opposite of what you might think right here. Okay. So that's it. And again, really all that's mattered for the C over B is the name. We'll talk about what that means in a bit, but let's do some examples talking about it. Example 4, identify, let's do two things. Part 1 is going to be the direction and magnitude of the phase shift. Also, mathematicians are notoriously lazy. I will probably almost always be calling this PS. All right. Identify the direction and magnitude of the phase shift and the vertical shift. All right, we're going to incorporate points 3 and 4 at the same time. Yeah. Okay, so let's do these, and then that'll be it for the day. Part A is going to be f of x equals sine of x plus pi over 6 minus 2. So remember, phase shift is always opposite of what you think it's going to be. It's going to be this number divided by the coefficient of x. So the phase shift is going to be pi over 6. That's our c here in the formula. Remember the standard form of a sine equation, of a sine graph. We're going to be talking about it is like this. So it's going to be that c divided by b. b is the coefficient of x, which is 1. But wait, hold on. Something's not right here. In this formula, there's a minus. this formula, there's a plus. Remember, it's always going to be opposite of what you're going to think for the phase shift. So it's going to be negative pi over 6, right? In the formula, we're subtracting here. We have to flip that. So it's a lot of stuff, but it's essentially negative pi over 6. So we're asked the direction and the magnitude. So negative means that we're going to be going to the left, and the magnitude is pi over 6. Okay? So our answer is going to be left pi over 6. Is our answer for little part 1. Okay? And this is a bit confusing. But the more and more of these you do, the more you'll get used to it. Math is learned by doing, okay? That's why I make such long homework assignments. It's not to torture you. It's so that you get practice doing it. And as the more you do it, the more second nature it's going to be, okay? Just like when I ask you what's 2 times 2. You're not going down and say, hold on, let me get a piece of paper and a pen. 2 times 2 is going to be, let's see, we got 2 down here, 2 down here. Let's see, we got 4. No. You've done 2 times 2 so many times, you know right away that I can't snap while I'm holding a pen. It sounds like this garbage. You just know it, okay? And math is a lot like that, even more complicated math, okay? So practice is important. Part B, g of x equals 3 cosine of x minus pi over 2. Oh, oops, I didn't finish. Oh, we didn't talk about the vertical shift. What's the vertical shift here? Again, you might say, oh, it's 2. But remember, right? It's plus d. It says up d units. Sounds like one of those stupid jokes that I'm not going to talk about. Never mind. That's a story for another time. So this is minus 2. That means it's going to be down 2 units, okay? So let's incorporate that here. Down 2 and left pi over 6. So similarly, again here, the phase shift is going to be, we already have the negative right here. So now our phase shift is going to be positive. Positive C means negative phase shift. Negative C means positive phase shift, unless there's a weird thing with B. Okay, so it's going to be just pi over 2 divided by the coefficient of x again, which is 1. Right? That's just pi over 2. Anything divided by 1 is itself. So that now tells us that it's going to be right pi over 2 units. That's what the phase shift tells us. All right, and this is kind of hard to read. There's supposed to be a plus 1 right there. So we are moving up 1 as well. That's the vertical shift. All right, and let's finish off this example with part C. H of x equals sine of 2x plus 1 plus pi. Oh yeah, we got a b now. All right, save the b's. We care about b's here. Well, we had b's here too. They were just 1. We want more b's, okay? Or at least a bigger b. So again, we just follow the same thing. Phase shift, opposite of what you might think for phase shift. Hold on, can I make this connection? No, I can't, never mind. I was gonna make an observation, but it's not true. So I don't want to say things that are not true. So the phase shift is going to be opposite of C. Okay, so negative, well, technically it's just C, but it's going to be the opposite of what you see. All right, divided by B. I wrote C. I meant to write 1. C, there we go. It's negative 1/2. Okay, which means that it's going to be left 1/2. Okay, and again, the vertical shift is up whatever plus this is. So it's going to be up pi units. All right. So again, I don't want you to think me a liar. I'm going to prove this to you. Okay. So remember what our answers were. Let's see. If we just look at some graph of sine x, again, I want to see this. So green or blue is going to be the sine x. All right, so let's do things one step at a time. Let's look at the phase shift for part A. So in part A, what we did is we had an added pi over 6 on the inside. And what we said is, okay, the phase shift is negative pi over 6. We said we're moving the graph left pi over 6. So is the green graph the same as the blue? Just move left pi over 6? Well, let's look at it. 0, 0, negative pi over 6, 0. It is the same thing, just moved left pi over 6, exactly what we said. And then we said there was also a vertical transformation here. All right, there was a negative 2 on the outside. Well, does that move everything down negative 2? Yep. Here we were at positive 1, here we're at negative 1. Here we're at negative 1, well, now here we're at negative 3. So the vertical shift is as we said. The phase shift is as we said. Okay? And we could do this for all the other ones, but I think at this point you should have a good idea and be fairly comfortable with what's going on here, okay? So, I don't often do this, but just like a TV show, to keep you okay over the weekend, we have a little teaser of what's to come. So this is what we did today. First page of my notes. Tuesday, we got some really good stuff. Okay. We're going to do it all at the same time, doing all things together. This should be pretty easy. And then we're going to look at some graphs, and I promise I'll draw them nicer. These are just my scratch notes. We'll look at how to find some graphs from a given sine and cosine function. All right. And then we're going to be graphing ourselves, and we've got some really neat application problems. It should be pretty fun. So you are in for a treat. Again, technically right now you have everything you need to do the homework. You can do the whole homework if you wanted. That'd be great. But we'll talk about a lot more stuff on Tuesday. But we got the facts. Most important part of this section by far, these four points. Period, amplitude, phase shift, vertical shift. What does it all mean? Feel free to use Desmos to check your answers. All right. Anyway, thanks for watching. Have a good weekend. Good luck on the exam, which you should be taking soon. Bye.